Welcome to the fifth video in the linear algebra series. In this video I will talk about determinants. So before I do so, I have a little bit of a disclaimer. So the actual definition for the determinant of a matrix is a very complicated expression, and it is beyond the scope of this lecture and beyond what you will ever need to know in real life applications. So we will not go over that here. Instead, to compute the determinant of a matrix, we will use a theorem which is called, the method of computing is called cofactor expansion, and this is what I will show. I will not show the actual definition, and we will basically just use this theorem as the definition of a determinant. So yeah, as I said before, we will show how to compute the determinant by cofactor expression, and as you can see, this is quite a big theorem. So let A be an n by n matrix or a square matrix. The determinant of A is denoted by det A, or we can also denote it more explicitly. So we can put these square brackets around our matrix. Then we denote the matrix with row I and column J removed as Aij. And then we compute the determinant of A using this rather hefty formula. So, or algorithm I should say. If n is 1, then the determinant of A is A11. So, for example, if A is this 1 by 1 matrix, its determinant is 0. If n is greater or equal to 2, then we get this formula. So the determinant of A is this sum with alternating signs of entries of A multiplied by the determinant of A with row I and column K removed. And this is the same as removing row K and column J. So, what is this? It is much easier to see an example where this is computed than to go through and explain where this formula comes from, so I will just do that. So we have this nice 2 by 2 matrix, and we want to compute its determinant. So we first write that down, and we want to perform cofactor expansion. And the nice thing about cofactor expansion is that you can choose where you start your expansion. So you can pick any row or column where you want. And basically what you do in your mind is you pick, for example, let's pick this A. And then we say this A is in position 1, 1. So we write down -1 to the 1 plus 1. So that's I plus J. Then we multiply by the determinant of the matrix, which has the column and row in which A is located removed. So we, in our head, remove this column and this row, and we are left with this matrix. So just D, so D, but the determinant of D is just D itself. And then we have to remember to multiply by A, because that's the coefficient that we started with. Then we go then along this row, because we've chosen this row for our cofactor expansion. And we take -1 to the 1 plus 2, because now we're in column 2. We, again, imagine removing this and this, we are left with C, and we multiply by B. So, as you will see, this is also what I have here. Actually, here I wrote A11 and A21. Actually, I should have written determinant there. That's a mistake. Anyway, you get what I mean. So, and what we then obtain is AD minus BC. And you might have seen this formula before. So you can memorize this if you want. You multiply this by this, and this by this, and here you put a minus sign. Okay, let's look at another example with some numbers. So here we see this matrix A, where we have this nice row here with a lot of zeros. So in our process of cofactor expansion, we always multiply by the coefficient of position of where we are. So if we can somehow select this row, we only have to do one calculation in a way. So this is exactly what we do. Is we select this this row here, so we can then simply just only look at the multiplication that happens through this one. So that is the determinant of this matrix here. So you see that one here. And if we work this out, we plug in the -1 with the proper exponent, and we multiply by 1, that's this one, we find -5. We could have chosen any other row or column to expand along and would have found the same answer, but this is just the easiest one. So when calculating a determinant, you should always look for zeros or some other structure in your matrix that allows for easy computation of the determinant. Now, we move on to covering some properties of the determinant, which are nice to know. So first, let A be a square matrix. Then the determinant of A transpose is the determinant of A. If A has a 0 row, then the determinant of A is 0. This you can understand by the freedom that we have in choosing our cofactor expansion. So if we choose to cofactor expand along the 0 row, then we will just find that everything is multiplied by 0 and everything added up, it will just be 0. If n is greater than or equal to 2 and A has 2 identical rows or columns, then the determinant of A is 0. The way of showing this basically follows from another theorem that shows that in which you can show that you can use elementary row operations, and this creates a 0 row, and then you can use the second condition in a way to show that the determinant is here also 0. Then we also have a new characterization of non-singularity, which we can add to our list of equivalent conditions. So the square matrix A is a non-singular if and only if the determinant of A is non-zero. So by negating this, we have that A is singular if it has 0 determinant, or if and only if actually. So let's look at an example of this. So we have this linear system, and we want to know if it has a unique solution. So what we do is we write down its coefficient matrix A, and since this n, it's a 4x4 matrix, so n is greater than or equal to 2, and A has 2 identical rows, so that is this one and this one. So by the previous theorem, we see that A has a 0 determinant. We saw before this was equivalent to non-singularity, and if you recall back to the video about non-singularity, you will remember that one of the equivalent conditions for non-singularity was that the system, for every b, the system ax equals b has a unique solution. So since this matrix is singular, this means that the system either doesn't have a solution, or that if it exists, then it is not unique. Yeah, so that's exactly what I wrote here. Okay, that concludes the section on determinants. In the next video, I will talk about eigenvalues and eigenvectors, which are very, very important for engineering.